Let's dig a bit deeper into this problem of why lock has failed. The lock variable, this lock solution failed because of this. See this? Now we are loading the lock value into R naught and then comparing and then doing some comparisons, and after that we are setting it here, right? Now it failed because once a process has loaded the value and once it gets preempted after step 1 or step 2 or step 3, which means any process which has loaded the value and if it gets preempted before storing it, right, then some other process coming in the middle and is also loading the same value, and therefore these two processes are getting inside the critical section. Now if you want to stop this from happening, you should not let anyone come in the middle, right? So I was just wondering, what if I write this line and immediately this line and then these two lines, which means you just think about it. What if I write like this? If I write like load and then lock R naught, which means I am loading the R naught into, lock variable into R naught, and then the next step is store the value 1 into lock immediately, which means whatever was the previous value of our lock, I am loading into R naught and I am setting the new value 1 into lock, so that even if after some time if someone reads the lock, they will immediately see as 1. Are you trying to just understand this? What is that I am trying to do is, I am going to load the value of lock into R naught, either it will be 0 or 1. Anyway, either it is 0 or 1, I don't care what it is right now, I am simply making it as 1, which means you are actually saying that I am locking it, right? I don't care what its value is, I am again locking it. In case if it is already locked earlier, it doesn't hurt, which means if the earlier value of the lock is 1, again you are storing 1 into it, no problem. In case if the earlier value of lock is 0, then only you will get that 0 and immediately you are locking it, right? Therefore you are decreasing the chance that anyone will come in the middle and see the value of 0, right? And once you have locked it completely, which means once you have set 1 into the lock, then you can do the comparison at your own time, isn't it? So which means you can compare whatever you have loaded initially, either it will be 1 or 0, now you compare it, right? And in case if it is 1, right, which means if it is not 0, if it is not 0, then which means if it is 1, again you go and load and do the same thing, right? So this one and this one both are same. Check it. Here what is that we are doing? We are loading the value of lock into R naught and then comparing it and then storing the value of 1, right? And what is the comparison you are doing? You are comparing with R naught, right? Here also the same thing we are doing. We are loading the value of lock into R naught, but then immediately we are storing 1 into the lock and then we are comparing R naught with 0, right? And if it is not 0, then we are going to go back. So both are actually same, right? So what is that I am trying to do here is, see, in terms of room, I think you'll understand it better. Again, going back to the dressing room example, right? So initially there is some tag, right? I don't know what that tag is. Either it will be vacant or it will be occupied. Fine, I don't know what it is. Then what I do is, before I enter, right, I'll take this tag and I'll keep it with me. I'm going to take this tag, remove it, okay, completely removed, and I'll not see it then. I'll keep it in my pocket, the tag, right? Either it is vacant or occupied, I'll keep it in my pocket. And then what I do is, I'll put a new tag there that it is occupied. If it is occupied earlier, still you are putting it as occupied. If it is vacant, still you are putting it as occupied, right? Now anyone who sees it will not enter it, isn't it? Now what I do is, after that, now my pocket contains the old tag, right? New tag I placed it as occupied. Now my pocket contains a new tag. Then I'll take out the new tag and I'll see it. Oh, now it is vacant. Then I'm going to enter it. Now in case if it is occupied, then I'll not enter it. Got it? The same thing I did here. So what is that? Now I'll see the old tag, right? Keep it in my pocket, which is nothing but R naught, and then I'll put the new tag there, which is nothing but 1 is placed in that, which means occupied. And then I'll compare. Later I'll open my pocket and I'll see what it is. If it is actually 0, then I'll enter it. If it is actually 1, I'll not enter it, right? Now by doing this, do you think that again, is there any probability that two people will again enter the room at the same time? Still there is a chance. How? The reason is, now you might have taken this tag out, isn't it? And then before you put the next tag, right, if someone else comes here, then again they'll enter, right, which means there'll be no tag at all, which is nothing but tag is 0, kind of it. So I cannot explain you in this example, but then in this one what the problem is, watch it. Now P1, let us say process 1 has executed line number 1 and then got preempted, and now the process P2 has come for execution, and now process P2 has executed line 1 and then line 2 and then line 3, 4, and then it entered into critical section. And later what happens, again P1 will enter and P1 will execute line number 2, line number 3, line number 4, and both of them will see initial value as 0 itself. If the initial value of lock is 0, P1 will see R0 as 0 and P2 will see R0 as 0, right? Which means again if the preemption takes here, then there is a problem, right? Earlier if the preemption takes place here, here or here, there was a problem. Now if the preemption takes place here, again there is a problem. Still the problem is not solved. Then how can you solve this problem? The only way to solve this problem is, you should see that after you load and before you store, there should not be any preemption, which means these two instructions should be executed as a atomic operation, right? If you could make these two as atomic operation, right, then this problem can be solved, which means now you are looking at the loading the value of lock into R0 and then you are setting the lock value as 1. Between these two there should not be any preemption. In case if there is any preemption between these two operations, you will be in a trouble, right? So for that reason we need some support from the platform, which means the platform, the operating system and the hardware are supposed to provide you with one special instruction, and some of the platforms they provided, that is called TSL, test set lock. Now what will this test set lock will do is, if I write TSL lock R0 like this in place of these two operations, what it will do is, it will load the value of lock into R0 and then it will set the value of lock as 1 in just one single atomic operation. These two instructions can be replaced with one single instruction. Therefore no one can enter in the middle, right? So by replacing these two instructions with this one instruction, we can still use the lock variable without any problem. Check this. How it will work is this way. Now this is instruction number 1 and say this is instruction number 2, this is instruction number 3 with TSL, right? Now if P1 executes instruction number 1 and gets preempted, then what happens? The lock value is definitely 1. And even if P2 comes and executes instruction 1, it will find out that lock value is 1, right? Even though when it tries to go to 2, it will see that it is 1, and therefore it will again execute 3 and again 1, again 1, 2, 3 and again 1, like that, 3 and 1, right? Therefore only one process will enter into the critical section. The process which will enter the critical section is the one which executed the TSL instruction first. So if any process has executed TSL first, later if some other process comes and looks at the lock value, it will always be 1, right? So this is what is TSL, right? So now let's examine. Yes, obviously mutual exclusion is guaranteed, because at any time only one process can see the lock value as 0, and once it has seen the lock value as 0, it is changing it to 1 without giving any chance for others to look at it, right? It is like this. Now you are going to the room, and whatever it is there, you are immediately taking it out and putting it as 1, right? Therefore if it is 0, only you will have 0, then you can enter it, and next time if anyone comes, it will always be showing as 0. Why? The reason is, now once you take the tag out and then putting the next tag, this is done as an atomic operation. No one can stop you from replacing it. Therefore once you take 0 and put the 1 there, right, then you are very sure that your 1 is always going to be there, right? Therefore if next time any other process comes and when they take the tag out, they will see 1 and again they are going to put 1, obviously they are not going to enter it. So only one process is going to be inside it, right? Therefore mutual exclusion is definitely guaranteed, right? And then what about the other condition, the second condition? So what is second condition? Progress. So progress, what is progress? If a process doesn't want to enter the critical section, then it should not stop others from entering it. Obviously progress is guaranteed. The reason is, if a process doesn't want to enter the critical section, it will never execute TSL. If no one is executing TSL, obviously lock will be 0. Therefore only the process which wants to get inside the critical section will get into it, and other processes will not get into it, right? So therefore it is providing, TSL is providing mutual exclusion as well as progress. Both are being provided. What about bounded waiting? Bounded waiting, that depends. Why? The reason is, some process might be very unlucky that whenever it gets a chance, someone will be there inside the critical section, right? And then later if someone else gets a chance, again later when it comes out, some other process might get inside. Therefore bounded waiting is not guaranteed, which means we cannot say that one process is going to get a chance after some amount of time. Therefore there could be a starvation in this case. A process might be so unlucky that, which means it is like this. See, it is like this. Someone is inside the room, right? And now you are waiting outside, and later you are preempted, and this one comes out, and then someone else might enter it, and again you come and you wait, and again they go out, again someone else enters, and again you come and wait. So a process might be so unlucky that it might get starved. Therefore starvation is always there, and moreover it is not portable, or architecture neutral, which means your platform is supposed to provide you with the TSL instruction. Without TSL instruction, what I mean to say is, if you don't have this TSL instruction, right, then you will not be able to implement it. For that you need the support from the architecture. This TSL instruction should be provided by the operating system. If it is not there, you will not be able to execute it, because if these two instructions are not provided in an atomic way, implementation is never possible. Therefore it is not architectural independent. It is dependent on the architecture, right? So the second condition, the third condition and fourth condition, they failed, but even that is not a big thing, because the main conditions are mutual exclusion and progress. They are guaranteed, and you need not worry about the second two conditions, right? But then there can be one more problem called as priority inversion problem. Priority inversion, right? Priority inversion. So priority inversion means like this. Let us assume that there is a process P1. Now this is the entry section, and this is critical section, and then this is the exit. Now the entry section is implemented using TSL, right? Assume that there is a process P1 which is having priority 0 and which entered critical section, which means process P1 is in the critical section, and suddenly a process P2 has come whose priority is higher than process P1. Let us say its priority is 1, and now P1, since P2 has come, right, P1 will be preempted by your scheduler. If you remember that scheduling algorithms, whenever I get any process with higher priority, the process with lower priority will be preempted, which means P1 is still in the critical section of execution, but then it will be preempted by the CPU. Therefore P1 is in the waiting queue now, and now P2 will be scheduled, and let us say P2 is also cooperating with P1, which means P2 also wants to execute the critical section. Then it will try to enter it using the entry, right, entry point. Now entry point will block P2, right, which means our scheduler is trying to run P2, but our synchronization mechanism is stopping P2, right? Therefore P2 can never cross this hurdle, and P1 will never leave this hurdle, isn't it? It is like this. So P2 wants to get inside this critical section to finish its execution, but then we are not going to let the P2 go because of our synchronization mechanism, right? And then P1 will not let P2 get inside it, right? But then if are you understanding it? See, it is like this. CPU is with now P2 because of the priority, but the critical section is with P1 because of the synchronization mechanism. It entered first, right? Now see this. According to the priority scheduling, P2 is having the CPU because the scheduler is scheduling P2, but then P2 will not be able to cross the hurdle because P1 is inside the critical section, and we have written our synchronization mechanism in such a way that no other process will enter into the critical section as long as P1 leaves. See, P1 has left the CPU, it didn't leave the critical section. Even if P1 is not executing, as long as it doesn't come out of this critical section, it will not let anyone get into this, right? So now see this. P1 wants the CPU in order to finish it. P1 wants the CPU in order to come out of the critical section, right? And then P2 will not leave the CPU unless it gets into the critical section. Now both are in a kind of fight, right, or kind of lock, isn't it? Therefore it is a deadlock, and in fact it is called as spin lock, right? So deadlock is what? Deadlock means both the process will not execute, both the processes will be in the blocked state. But here both the processes are, one is in the ready state and other is in the running state, and both of them are locked. Are you understanding this? See, CPU is with P2 but critical section is with P1. Now P2 wants the critical section to finish its execution and then it will leave CPU, but then P1 wants CPU in order to leave the critical section. Therefore both of them are not blocked. Actually the definition of deadlock, I'll tell you later. Definition of deadlock is like this. It is a set of processes which are blocked, which are not in the ready or running state, which are blocked waiting for some resources, that is called deadlock, right? But then here it is, funny thing is, these two are not blocked. One is in the ready state because it just got preempted and therefore it is in the ready state, and other is in the running state. So this is called as spin lock, right? So that is the problem with the lock variable. So even though there is mutual exclusion and there is progress guaranteed, there could be a chance of spin lock, which is a kind of deadlock, right? So we generally don't go for this in case if you want priority, and generally we have priority in many cases, right? Priority scheduling in many cases. If you are using round robin, then no problem, no issues, because using round robin at some point of time again P1 will get a chance, and anyway it is going to leave the critical section. But with priority algorithm there will be a problem with this. Got it? So now with the lock, instead of using the lock variable directly, if your operating system is providing TSL, go with this, but then it has got this problem. Anyway, it is up to you whether to implement it or not, because depending on the scheduling algorithm you should choose it. Okay, fine.